Welcome everybody in the lecture hall. Welcome everybody on Zoom to this new lecture. So today we are actually going to go into formalism, especially the formalism of the relational model. So last week was really an appetizer, a very high level view of the menu. And so today we are going to actually do a lot of math. It's a theoretical heavy lecture. Next week will be practical again. Then the week after that, theoretical, then practical. So I will alternate a bit between the two. All right. I will start as always with a question. So you can go to this address right here, the same as last time, or install the app on your smartphone. So switching over to this. And my question is, what is the name of the principle posited by Edgar Code in 1970, according to which the user should not be exposed to the implementation of a database system, more exactly a database management system? All right, so we have a majority, and the majority says data independence, which is in fact the correct answer. So congratulations. Oh, I understand what's happening. All right, so let me switch back to the slides. All right. So data independence is indeed the idea in 1970 that I told you about last week. It's this idea that the way that people were doing data querying in the 1960s, meaning that they had files like CSV and the like on the hard drive. I don't know if it was CSV back then, but basically the data stored in files. And they were using languages in order to directly read the files and then manipulate them and extract information and so on. That's very complex because there's a lot of complexity, a lot of burden on the shoulders of the user. And so Edgar Code said, as I explained, that the user should only have to think in terms of tables, selection, projection, and the like. And that's it. And the rest is hidden and nicely encapsulated. It has a lot of virtue, as we will see during this lecture. Tables are not the only shapes. I told you there's 5 in total. So there's trees, cubes, graphs, and unstructured data. But in this lecture, we will focus on tables. Almost the entire semester will be focused on tables and then cubes at the end. Trees are covered in big data for engineers, unstructured data in information retrieval, which is a computer science bachelor's lecture. And graph I cover it at the master's level for computer students. It's yet another kind of shape. Okay, but today we will bother with tables. So in order to define a model, because today's lecture is the relational model, we need to say what we manipulate and what we can do with it. So what does data look like for the model? The fancy name for a table is a relation, we will see why, or a relational table. That's the full-blown name. So what we'll do today, we'll try to mathematically capture this as something less hand-wavy than just this is a table. The second part, which will be in 2 weeks, that's called the relational algebra. That's the manipulation primitives in order to turn tables into other tables. It's like the addition or multiplication on numbers. We'll do the same with tables, but we'll see it's not addition, multiplication, it's called something else, right? Selection, projection, and so on. So this is what we do today. This is what we'll do in 2 weeks. Why tables? Again, tables are thousands of years old. This is a clay tablet that I showed you last week. It was found in Mesopotamia. It's been used for 3,800 years. This is enormous. This really means that this is very intuitive, and it's something that humankind realized very early, that you can organize your data in rows and columns like this in a structured fashion in order to write inventories, accounting, and so on and so on. And everybody understands it. It's even easier and more universal than pie charts, for example, or scatter plots. And it hasn't changed much. I mean, I don't really see much difference here, except that maybe here you can also swipe around and so on, but basically it probably feels the same. So this is Edgar code, just so that you see what he looks like. And data independence means that we have this model that we will describe mathematically today, the relational model. That's a logical model, would be pure math today. It will be implemented physically with C++, Java. So of course, the implementation of the actual system that maps it physically that the user doesn't need to deal with is done in an imperative language. At first, we will not really worry about this in most of the lecture. We'll work on the logical level because this is what the user sees. At the end of this course, in one of the last weeks of the lecture, we look a bit into the physical implementation of it, how it actually looks like physically on the hard drive. And because of data independence, you can change what is in there. This is an implementation of a relational database management system. This is also an implementation of a relational database management system, even though probably back then they didn't call it that way. Right, but this is essentially what it already was. Okay, so let me start with this high-level terminology that people use sometimes in everyday life. In particular, what might be confusing at first is that there are several words to describe the same thing, but actually it's the same. So I'm giving you the synonyms just so that you know. I'll try to be rigorous in my use of the words today, distinguishing between the mathematics and the database level. But basically, we have the notion of a table. We'll call it a relational table today. It can also be called a collection in some of the systems, especially NoSQL systems that deviate a bit from the normal forms. So table or collection, you can basically, the reason for collection is that you can see a table as a collection of rows. And these rows have plenty of other names. So one row is like this, right? It's a horizontal slice of a relational table. Some other people, these are the business people, they call it business object, right? Everybody understands what a business object is. So this is a business object. Some systems call it items, some other systems call it entity, some systems call it document. This is especially in NoSQL systems. Record is the word that I'm going to use a lot today. Tuple I will also use today, but tuple is a mathematical concept. Record is the database concept, right? One way to define a record, as we will see, is as a mathematical tuple. That's why. But in everyday life, a lot of database people still use the word tuple, even having forgotten about the mathematical meaning of it, right? It's just all of these words basically can be used a bit interchangeably, right? Then we have the vertical slices of the table. They are often called attributes, but it can also be called column, right? Just like that's probably what most people, even outside computer science, would know it. Field, property, especially in NoSQL systems. And key is also another way of calling it, but this is maybe less accurate because, in fact, when we use the word key, we usually mean the one column that identifies the rest of the table. An example of that would be if this is a table of people with one person on every line, the primary key could be the social security number, right? Because the social security number uniquely identifies a person. with any country. So in that case, the social security number is of course an attribute, but it's a special attribute that is also called a primary key, also called a row ID key. You see that's a lot of terminology, but I put in bold some of the most common ones. All right, but this of course was not formal. This was just a high-level description of the concepts that we want to define mathematically, and we yet have to define it formally. So if we look at it like cooking, you need ingredients, and then you need to mix the ingredients together in order to bake a cake, right? A tasty cake. So our ingredients are basically, if you look at the table here, we have the attributes here. These are the headers of the table in a spreadsheet software. That would be the first row. And then we have the values. In every cell here, we have a value. So if we really bring that down into pieces with the elementary ingredients, we have attributes and we have values. And now we need to come up with some math that's going to give a structure to how the attributes and the values are assembled in a way that looks like that. Right. So this is what the math is going to do. All right. So now, before we go into this and we come up with the definitions, I would like to make sure that we are all on the same page regarding the math. I assume that many of you will already know what I will show now, but some of you might not. So I just want to make sure that if you don't have a heavy mathematical background, even though you might have seen a bit of that in high school, that we are very clear on what is meant here. One of the goals is also that, I'm in the computer science department. Computer scientists might not, it's like physicists, we might not use math in the same way as fundamental mathematicians, right? And some of the concepts might be also computer science words. So let's go. So first, there is the notion of a set. So a set is, you can see it as a bag, even though I shouldn't be calling it a bag because it means something else, as we will see. But basically, it's something that items can be a member of, right? So for example, it's better with an example. This is the set of all the natural integers. It has 0, 1, 2, 3. All of them, it's actually an infinite set, right? But it has the as its element the natural integers. So a set can be basically a set of anything, and in fact it drove mathematicians crazy in the 19th century, because then they also started to ask questions: is a set a member of a set? Can a set be a member of itself? And so on and so on. And actually it causes a lot of problems. But let me show you another example. So this here is something that would be computer sciencey. So this is mathematics, right? Because the natural integers are mathematics. Who knows what a string is? Who doesn't know what a string is? Don't hesitate, right? Seems like nobody. Okay. So a string is something you see in computers. It's whenever you have text, it's basically a sequence of characters, right? So the term for what it actually is, the fancy term, is that it's a monoid structure with respect to concatenation and the empty string as the neutral elements. So that's if you want to sound fancy. But basically, this is the set of strings. The set of all the strings that you can imagine. This is the empty string. So they're usually with double quotes on either side. So this is the empty string. This is a string with 3 characters, FOO. This is a string with 3 characters, BAR. And then you can imagine longer strings. You can even have strings with new line characters, right? Like an entire book would be a string, for example, unformatted. All right. The set of all strings is going to be very important today. Why? Because, for example, the possible attributes that we can have will be strings. So this is why. So this is the set of all strings. Now, when you have a set, you have a relation between any mathematical object and that set. This relation is a relation of membership. You ask, given X, does X belong to A? Is X a member of A? If it is the case, then you write X belongs to A. If it's not, then you just add some crossing line in there that says is not a member of A, right? But basically, X is a member of A. And what drove mathematicians crazy in the 19th century is, in fact, that because you can ask for any mathematical object if it's the member of any set, if you really try to go the whole way with absolutely any mathematical object, you run into all kinds of contradictions. When I say that it drove mathematicians crazy, it literally drove mathematicians crazy in the 19th century. But fortunately, there's a reason why it's not a problem for us in database lectures, is that in a computer, everything is finite, right? There are only so many bits that you can have in a computer. So that kind of gets rid of the problem for us, and we can just view it without worrying about these things. For example, the number 1 is a member of the set n, like this, of the natural integers. All right? Okay, and likewise, the string foo, double quoted, so FOO, is a member of the set of all strings. Okay? The next notion is the notion of subset. Given two sets, A and B, you can ask the question, is A a subset of B? Or in that case, B a subset of A? So B is a subset of A. It's very intuitive with this picture right here. This is B and this is A. If all elements of B are elements of A, right? So in that case, you denote it that way. So typically in the English convention, you have this inclusion element together with an additional horizontal line here. The reason that's actually depending on the country. In some countries, you don't have this extra horizontal bar. What it means is that B could be A. So for example, A is also a subset of A. In fact, A is equal to A. So the horizontal lines say that it could potentially also be the entire set A. All right? Okay. Here's an example. If you consider the set of all natural numbers and the set of the even natural numbers, then these numbers, the set of these numbers is a subset of the set of the natural integers, right? So in that case, I have the graphic with all the even natural integers are here. The odd are outside of this subset, but still in the set n. So the set of the even natural integers is a subset of the set of the natural integers. Okay? And another example here is that we might have a set of strings that are university names, like ETH Zurich, Stanford University, PFL, and so on. And the names, the set of the strings that are the names of a university is a subset of the set of all strings that we will call S in this lecture. All right, so there are a couple of common sets that we will be using because it's actually quite convenient. Some of them are general conventions in mathematics, like for example, B for Booleans, true, false, that everybody uses. D for decimal numbers, it's everything with digits and a dot in the middle, possibly negative. This is the set of the natural integers, right? The one you use for counting. The set of string is my own convention. This is not a convention that everybody would use, but I just use it conveniently here as the set of the strings. This is also a convention in my lecture that the V in that way is the set of all possible values you can see in a table. In particular, that includes numbers, strings, decimal, and so on. It's basically all values. And we'll see a bit later that actually very often we restrict ourselves to atomic values, but don't worry too much about that. I'll explain what this is a bit later, right? But basically, this is the set of everything that could be in the cell of a table. And T I will use as the set of the relational tables as we want to define them. All right, who is following for now? Okay, very good. Do not hesitate to ask questions. Again, for most of you, I'm sure you already know that. I just want to make sure that it's for all of you that you will follow what I'm saying next. Okay, so this is a set. Now I'm going to do a bit of computer science things. In computer science, we also have the notion of set. Yes, go ahead.
Oh, it's a microphone. Okay. Just a clarification on the.
Maybe the volume needs to be.
Okay, just a clarification for the set of decimals. Is it intended as the set of floating point values, like say with finite precision or something, or do we count also periodic numbers and irrational numbers in there?
I see what you mean. So the set that also contains numbers with infinite precision, periodic number that would be called rational numbers, and also irrational numbers, that would be R. It's the set of the real numbers. So D as the set of decimal numbers really means the finite precision numbers. It's the ones that can be written in base 10 as a finite number of digits exactly, right? With the decimal period anywhere, right? The decimal numbers, this is an official notation. So mathematicians, I think they also use D for that. But in computer science, it's very important because we actually have that in databases. You can actually define the numbers in a column to be decimal numbers with a finite number of digits. In other words, these are all numbers that can be written as an integer divided by a power of 10. You can also put it that way, as a fraction. The numbers that are fractions, that would be Q, the rational numbers. R would be for everything. Right? Did I answer your question? Okay, awesome. So of course, R is not realizable in computer science, right? Because you would need infinite capacity on a computer, and the size of a computer memory is actually limited, right? Very good. Okay. So now, sets. Sets is a mathematical notion that was invented mostly or formalized in the 19th century, or at least gained interest. Computer scientists love sets too. In fact, in many programming languages, you have libraries that allow you to have sets. And you can add something to a set, you can remove something from a set, and so on and so on. You can test membership in a set. This, in computer science, is called an abstract data type set. There are several others abstract data types that computer scientists love. Another abstract data type that is less common in mathematics, even though I'm sure mathematicians could use it, is the concept of bag. What's the difference between a set and a bag? The difference is that in a bag, elements can repeat. You could have, like, for example, here, twice the blue elements, twice the orange elements, twice the red elements. So the difference with a set and a bag is that you can have duplicates. You cannot have duplicates in a set. It's always a unique, you know, either it's a member or it's not. In a bag, you have what's called an occurrence information. All right? A third example of abstract data type that you find in computer science is the concept of list. Set, bag, list. The difference between a list and a bag is that in a list, you have an order. It's first this, and then second this one, then third this one, and so on. So a list mathematically would basically be a finite sequence of anything. It's a finite sequence. Okay? So said, bag, list, kind of put them together in your brain, right? These are three fundamental concepts, three fundamental abstract data types that you find in many programming languages. And again, going from a list to a bag, you just forget about the order, and going from a bag to a set, you forget about the number of occurrences. That's how to think of it, right? It's very important that you remember that, because we'll see that you can define the relational model either based on sets, on bags, on or lists, but more about that later. All right, for whom is that clear what a set, a bag, and a list is? Okay, very good. Okay. Next, the concept of a pair. A pair can be seen as a list of two things, right? So for example, we could have this pair here that is drawn with orange and green. That's a pair that we call P. And we have this symbol, the cross, that's the Cartesian product. So A Cartesian product B is the set of all pairs with the first element in A and the second element in B, right? For example, the pair ETH Zurich 20,000 could be even more now because the student number is growing, but ETH Zurich 20,000, that's a pair. Now realize the second comma is a decimal, is a thousand separator, right? So the comma in the middle is the pair separator. So ETH Zurich 20,000 is a pair that is a member of the Cartesian product of the set of strings and the set of natural integers. Why? Because ETH Zurich is in S and 20,000 is in N, right? So we learn two things here, the concept of pair and the concept of Cartesian product, right? So here's an example of Cartesian product. So we have a set A with two elements, green and red. We have the set B with two elements, red and blue. And we have the set A Cartesian product B with four elements. These are all the combinations, green, red, green, blue, orange, red, orange, blue. All right. Now, here I have to be careful because I'm saying it's associative for the purpose of this lecture and in the way we work with the Cartesian product. A pure mathematician would argue, no, it's not associative, but I will not go into that right now. It has to do with the nestedness of tuples and so on. But for the purpose of the lecture, we will consider that it's associative. And what that basically means is that we can actually do Cartesian products over a larger number of sets than just two. Here's an example of Cartesian product. That's the set of all universities. That's the set of the two Booleans. So the university's Cartesian product Booleans has all combinations, ETH Zurich true, ETH Zurich false, EPFL true, EPFL false, Stanford true, Stanford false. So you have all combinations. In fact, it's very easy to compute the total number of members in there. It's always the product of the number of members. So here there are 3 members, here there are 2. So 3 times 2 gives you 6. These are all combinations, right? And in math, that's called combinatorics when you actually compute that sort of things. Okay, now here's why I told you the Cartesian product is associative at the risk of shocking pure mathematicians. You can actually define n-ary, meaning with n sets, Cartesian products. It means that instead of just a pair with 2 sets, you have 4 sets, A, B, C, and D. So this is in A, this is in B, this is in C, this is in D. That's not called a pair then, it's called a tuple. It can also be called an n-uple, a 4-uple, a 5-uple, a 6-uple, depending on how many you have. But the general term is tuple. Right, so this is in A, this is in B, this is in C, this is in D. And this here is the Cartesian product of A, B, C, and D. And this is the set of all possible tuples taken from these sets. All right, this is an example. If I take the Cartesian product with strings, 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 and natural integers, D-inf ETH Zurich CAB 8092 is a tuple that has 4 elements in that tuple that is a member of the Cartesian product between strings, 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 and natural integers. For whom is that clear? All right. Now you might have observed that this word is not new. I actually had it earlier as a synonym for row. That's not a coincidence. We will very soon see why. Okay, the next concept we need is the concept of a function. A function is defined between 2 sets, A and B, and it's basically all about the arrows here. A function associates every member of A with a member of B. Here to here, here to here, and here to here. There's only one arrow from each element in there. This is often denoted as here with this arrow. So F here, that's this is F. It's a function from A to B. And there is this alternate notation. You should avoid it if you don't want to confuse people, but actually it's a very, very nice shortcut. It's B to the power of A. So a set to the power of a set actually means that it's the function from A to B. But I will avoid this notation and use this one instead. Okay? So for example, you can also use this notation in order to say that this green element is mapped to this blue element. You say green element and you use this arrow with the vertical bar here. That basically means that the function is associating this with that. Okay, so this is functions. Here's an example of function from universities to cities, right? ETH Zurich mapped to Zurich, like here. This is how you would write it down in mathematics. EPFL mapped to Lausanne. UCL mapped to London. UZH mapped to Zurich, okay, University of Zurich. So this is an example of function, okay? Next, map. Mathematicians know this as a partial function. Why partial? Because it's the same thing, except that it's okay if some of the elements here are not associated with anything. This one here is not associated with anything. There is no arrow coming from there. This is why it's called a partial function. Computer scientists would call it map. They would call it map, right? So I'm going to call this a map because we are going to do computer science. So the difference of notation is that if you want to say that it's partial, meaning some members might not be associated with anything, you cross the arrow here in the middle, right? Vertically or oblique or whatever. So this is the set of maps from A to B, and you still have the same convention to say that green is associated with blue. All right? This is an example of map where city is associated with Zurich. So here, city Zurich. Name is associated with ETH Zurich. Department is associated with DMAT. And birth date is not associated with anything. This is a map from strings to values. Why? Because it associates some strings, because it's partial, so some strings to values. So this is the set, I didn't draw them all, but this is the set of all strings, and this is the set of all values. And that map only associates 3 strings to some values. For whom is that clear? That's the map. Okay. I want to add something important, is that in a function or a map, it's totally fine to have these sort of things. It's totally fine if 2 of the members of the left go to the same element on the right. That's absolutely fine, right? In fact, if you don't allow that, what is it called? Does anybody know? Injective, exactly, that's the term. If you want to forbid that sort of thing, that would be an injective function. Right, we have questions, I think, maybe on Zoom.
Yeah, so why was the map not S to S, so strings to strings?
Ah, that's a very good point. Let me go back. Let me go back. That's, yeah. Yes, you would be correct. I could also have said it's from S to S. Oh, so sorry, no. This is why, because these are not only strings. This is 42. It's a number, right? You could also, of course, have said, because this is the limit of when you draw things, right? That could be the string with 2 characters, 4 and 2, right? So in that case, you could have said, okay, these are strings, and this is a map from strings to strings. This is absolutely true. The reason why in that example, I said it's from strings to any values is that maps from strings to values will have a lot of them today. This is a very specific kind of maps that would be relevant for us for databases and relational tables. So that's the reason why here I gave you an example from strings to values. Does it answer your question? Yes, okay. All right, next, relation. Function, map, relation. The difference between a map and a function is that in a map, some of the members of the left could be associated with nothing. In a relation, it's the opposite. You relax that condition and now allow for the elements on the left to be associated with multiple elements on the right. Multiple means 0, 1, 2, 3, anything. So this is a relation where this element is associated with these 2 elements of B. This element of A is associated with 3 elements of B, this one with just 1, and this one with just 1. It could also be with 0. That would be also absolutely fine to have nothing, right? So a relation is the most generic thing that you can have, right? So this is a relation, and mathematically, so this is a bit formal now, a relation mathematically can be defined as a subset of the Cartesian product between A and B. That maybe you can think as an offline exercise of trying to convince yourself of that. This here, this mathematical object, can actually be interpreted as a subset of the Cartesian product of A and B. This is a set of pairs, and every row here gives you a pair. That's a small hint to figure it out. All right. There is also another way to put it, just for completeness. You could also say that instead of being a subset of A cross B, you can define it as an element of the power set of A times B, right? Okay. So here's an example of a relation between strings and strings. So these are strings, and I'm associated ETH Zurich with Zurich and Singapore. Yes, absolutely. ETH has a campus in Singapore. EPFL Lausanne, UCL London, UCH Zurich. This is a relation, right? So R is a subset of the pairs of strings, or an element of the power set of the Cartesian product of strings and strings. Okay, now you can actually draw relations like this in a different way. Here, I drew it with a set here and a set here, and I drew arrows, right? For every association, I just have this line here that basically connects them. But I could do it differently. I could take one by one these black lines here and draw them as a sequence. In other terms, it's a list of pairs, vertically listed, right? First, second pair, third pair, fourth pair, and so on. So I can draw it as a list of pairs. In fact, I did it as a list here because there is an order. In fact, it would be more accurate to say that it's a set of pairs, right? Because the order actually in which you have the rows doesn't actually matter, right? But I'm just using the words that we define: set, list, bag, and so on. So this here is really the same thing. This here is the same thing as this. This is just two different ways of actually drawing it. This is an example here. You could define or visualize a relation of strings and strings like this. You just list the associations: ETH Zurich with Zurich, ETH Zurich with Singapore, University of Zurich with Zurich, UCL London. It's the same thing as this, right? I didn't list them all, but this here is the same thing as this. It's only a visualization difference, right? I just express it in a different way, okay? Now, you can also define relations not just on two sets, but on three or more. In that example, it's three. All you need to do is list tuples. So this is a three tuple, and just list them. So now the relation is a subset of A cross B cross C. You can generalize it to n relations, meaning that you just have a set or a list of n tuples, right? And it can be unary too. That's the mathematicians love special cases, right? So this is a special case of unary relation with just one single set, right? Okay. Okay. Next, the notion of predicates. One way to define a relation, instead of listing explicitly all of the tuples that belong to that relation, you can express it as a predicate. For example, you could redefine this one right here that we had here. You could redefine it. Instead of listing, you can say it's the set of all pairs with a university on the left and a city on the right, such that the university has a campus in the city. That would be an equivalent definition. This one is explicit. The other one is implicit. The proper terms are extensional, intensional, right? Okay, so this means you can define it with predicates, and a predicate just takes a pair and tells you true, yes, it belongs to the relation, it is in there, or the predicate tells you no, no, it doesn't belong to the relation. For example, the pair UCL Zurich, the predicate would say false. UZH Zurich, the predicate would say true. Okay, so that's an example that I gave you earlier, that you can define it instead as telling you whether or not it is in the city. So here this is true. ETH Zurich Lausanne is false. Okay, who is following? Okay. Okay, so now we are done with the mathematical wrap-up, but I just wanted to make sure that we have these concepts. Some of you might see it coming, right? Because you might have seen things that start resembling a table. Let's roll back a bit. Does it not look like a table to you? Who sees a table here? Many of you, right? In fact, this is one of the ways to define the relational tables. And this is why it's called relational table, because this is a relation. So I hope you have your first aha moment right here, because this is how we will start. And that would be the textbook definition of a table. So here I'm drawing the tables like with rectangular cells, you know, with 3 columns and all the rows. But in fact, that's your aha moment that I told you about. You could redraw this table here. I put colors in there as a set of 3 tuples or a set of tuples, right? In other words, what we did is that we defined the table here as a subset of the Cartesian products between the domains. Maybe you have universities here, cities here, and numbers here. So a table is a subset of the Cartesian products of the domains of the columns. In other words, it's a relation over the columns. Who sees that? Who feels this intuition? Right, okay. All right, so now we can start formally defining it. So a domain, what we call domain, is just a set of values. Domain is the word that database people use for what you can have in a column. So a domain can be the set of integers, can be the set of strings, can be a set of dates, and so on, right? So these are just a few examples. The set of decimals is also very popular, even though computer scientists also like to limit, like for example, only integers in that interval and so on. But that we'll come back to in a few weeks, all right? So you can even have domains, as I said, that are sets of dates, sets of times, even sequences of bytes if you want to save pictures in your table and so on. So these are domains. So now, I hope I'm not scaring you with that. We can define, given a family of domains, so you just pick the domains that you want to have in your columns. In the first column, a set of universities. In the second column, a set of cities. In the third column, a set of dates, and so on. These are domains. This here is a fancy way in mathematics of just indexing the domains. There's D1, D2, all the way to Dn, and that's just a fancy way of doing that. And so we define a relational as a subset of the Cartesian product of the domains, D1 cross D2 cross all the way to Dn, right? Which is abbreviated with this fancy product notation that this is equivalent. It's just from K, from 1 to N, we take the Cartesian product of the decays. So that's the same as this, right? This is the same as this. All right, so a relational table is a subset of the Cartesian product of the domains. Done. Who gets that? Okay, so that's the textbook definition of a relational table. So now we can come back to our example. This is in fact a relational tables with how many columns? 2, yes, I see a 2, yeah, absolutely. We have a question on Zoom.
There's a question about the last slide. Why a subset and not a set?
Oh, so a subset is a set. The notion of subset is relative to another set. What we are saying is that a relational is a set of tuples, and it must be, that set of tuples must be a subset of the Cartesian product of the domains. By saying that it must be a Cartesian product of the domains, you ensure that the first element belongs to D1, the second one belongs to D2, and so on, and the nth one belongs to Dn. That's why. But a subset is always a set. Does it clarify? All right. Okay, any other questions? Okay. So this is an example, and here that's an equivalent representation, right? This is if I list them as on paper, but I could also visualize it as a table. So now this is basically a set of tuples, a set of pairs, because in that case there's 2 columns, so a tuple is a pair then, ETH Zurich, Zurich, ETH Zurich, Singapore, and so on. And you can see that this table right there with universities and with Zurich is a subset of the Cartesian product from string to string. So in that case, I took the set of all strings, which is the way you typically do that. Technically, you could say, okay, yes, it's the Cartesian product between universities and cities, right? But in a database, you don't go that far. You just say, okay, it's a string, right? And it's up to the user to make sure that what you put there is actually a university name and what you put there is actually a city. All right. Now, not surprisingly, we can define a record or a row. So a row or a record is that. So I'm going to call it a record. So an element T in a relational table. So that's the relational table. Again, a subset of the Cartesian product of the domains. We could also say a relation over the domains. So an element in that relation is called a record, and we call it T for tuple, and we also denote it T1, T2, Tn. So we use as a subscript here the number of the columns, first, second, n. And so the tuple, either you say T or you list its components. It's an element of R, which, as one of you said over Zoom, R is a subset of that, so R is a set. So since R is a set, it has elements like the tuples. And that means for all i's, for all columns, 1, 2 to n, and for all for every I, Ti here, the ith position, the ith value, must belong to the domain Di. It's always the case. Why? By definition, because we defined R as a subset of the Cartesian product of the domains, all the tuples in R must have their values in the domains. This is essentially what we are saying here. All right, so this is a visualization of T, and we can live with this and go for a quick break, 15 minutes. So I'll see you at 11:15 in order to continue this lecture. Thank you.